Hello, this is a problem from Chapter 8 from the chapter quiz. This is problem number 19. All right, ladies and gentlemen, what I'm going to try to do is as many as I can possibly get done. I'm going to work through problems, and I hope that will help you, but it's only going to help you if you take my advice. And here's my advice. My advice is look at any of the problems that I work out. I want you to look at the problem in the book. I want you to do your best to solve it. Try to follow the pattern that I use and do your best. And then when you get to the end, if you get it right, that's great. You can also watch my video. They're going to be fairly short, and you can kind of compare and contrast how I did it versus how you did it. If you get totally stuck, of course, you can always watch the video, and I hope that this will be a good experience for you. The worst thing you can do, the absolute biggest waste of your time, is to just watch the videos and not do the problems yourself. You absolutely cannot learn how to do this material by watching me do it. It would be very much similar to watching me play the piano. And I don't care how many times you watch me play the piano, you're not going to learn how to play the piano. So please take my advice in this regard. Okay, so this is problem number 19. It's in chapter 8. Now, what you need to do, though, when you look at these problems is kind of do a little thought experiment, so to speak, and do not pay attention to what chapter that we're in. And let me explain why I say that. I've mentioned before, and I hope that you've observed this yourself, Chapter 8 and Chapter 9 seem very similar. And the reason they seem similar is they're both talking about hypothesis testing. The distinction is that in Chapter 8, we are comparing a mean to a population. We're asking questions about some sample mean. And in Chapter 9, we're looking at two different samples, and we're comparing the samples. So you got to come up with your own particular example that makes sense to you to try to crystallize this in your mind. For example, in a chapter 9 problem might be, does medicine A do a better job than medicine B? You're comparing the two medicines. You're looking at the means, trying to figure out, does one do better than the other? For a chapter 8 type problem, you're comparing a mean to the population, so you might look at it and say, well, what is the mean of this population? Is it less than this? Is it more than that based on this sample? Or you might say, is this sample of people different from the population? For example, you might say, I'm going to take all the Geminis and I'm going to compare their personalities to the population at large. Are the Geminis different from the population at large? Okay. Or you could say, are females shorter than the population at large? Okay. Do people that have a gun permit, do they commit more crimes or less crimes than the population at large? So those are the kinds of problems that we do in Chapter 8. Okay, so the problem is that when I give you a problem like this, when I say, okay, take a look at number 19 in Chapter 8, well, you already have an idea of what to do, right? You know that it's Chapter 8, and therefore you know basically what to do in this problem. Well, pretend you don't know that. Pretend that you don't know that it's from Chapter 8, because you need to be able to decide for yourself which techniques are applicable based on the problem itself. On the exam or in real life, no one's going to tell you, hey, this is from Chapter 8, right? So you need to be able to do that. So that's the caveat or the warning that I would give you. You got to be careful. Try to figure it out for yourself. Don't base your techniques or your approach on what chapter it's from. Okay, without further ado, let's take a look. Number 19 here. Heights of models. We're in this New York modeling agency. A researcher wants to know if the average height of female models is really less than 67 inches, as his boss claims. You take a random sample of 20. You have an average height of 65.8. Standard deviation is so-and-so. It gives you an error budget alpha. Is the average height of the models really less than 67 inches? And then they want you to use the p-value method. So we're going to use the p-value method, but I'm also going to discuss the other method too, just for teaching purposes. Okay, so now let me close this out. And here's the problem, okay? Now, I always do the best I can on these, given the constraints of time. I just didn't have time to write out every detail here, but I hope this will be good enough. So here we go. Heights of models. This was what we're given. This is a pattern I always use. I always write down what am I given, what am I supposed to find, and then I'll have a solution. Sometimes I'll have a little discussion. I'll have that a separate head note for that. Sometimes I don't. Do whatever is appropriate, whatever you think is appropriate. I recommend writing out as much as you possibly can. You'll notice my solution has 6 pages. Okay, and some of you folks will hand in 4 or 5 solutions on 1 page. I just don't think that's a good idea. I think you should write out as much detail as you possibly can. Okay, so I write down the information that I'm given here. If you look back at the problem itself, you'll see. So when you're doing this problem, you say to yourself, well, what information do I have? What am I missing? How do I use the information I have? Well, I observe that I don't have the population. I don't have the standard deviation or the variance of the population. Okay, so that tells me right here. Okay, if I did know. This is chapter 8, important formulas. If I did know the population variance or standard deviation, I would use the z-test. I don't know the population standard deviation, so therefore I use the t-test, right? Because that's what we learned, all right? So here's the t-test for we use that when we don't know the standard deviation of the population. Okay, so I've said that 3 times now. I don't want to be redundant. Sorry. Let me stop this now. Okay, so as you can see, I write this stuff down. I don't trust it to my memory. I write it down so that I can explain it to an 8th grader, all right? Or I can look at it a year from now, 2 years from now. I can look at this and I understand what's going on because I've written myself these comments. Okay, so we don't know the variance of the population. Therefore, we're going to use the t-test, and here it is. Our null hypothesis is that the mu of the population is 67. Our claim, our alternative hypothesis is that mu is less than 67. We're going to use the formula for the t-test. Here's the formula for the t value, the test value. Okay, there it is. Boom, we plug everything in. All right, we plug everything in and we come up with an answer. T is equal to negative 3.157. Okay, so now we need the p-value for this. Well, take a look at the cartoon. I'm telling you, if you don't draw these cartoons, you're making a big mistake. In general, this is what a t value or a t distribution looks like. Negative 3.157. Okay, that is right there. Give me one quick second. Okay, so we've got this test value, the test value of negative 3.157. We draw a little cartoon, okay, and this is where we are right there, negative 3.157. Okay, we need the p-value. So we need to look at the table at the end of this solution. We look at table F, okay, and by the way, it's degree of freedom 19 because the number of people in the sample, the n is 20, so the degree of freedom is always 1 less, so it's 19. Okay, so we look at the table at the end of this solution. So let me go down there. Okay, here it is. Okay, degree of freedom of 19. We come over here. We go as far as we can, as far as we can. Well, our table ends right here. This is the last value we have, 2.861. Okay, that is a one-tail test. Here's our one-tail test. Okay, all right. So what this is telling me is that, and it's symmetric, so it's negative 2.861. What we're saying here is that 0.005% is to the left of the negative 2.861. So it's 0.005. So now let me bounce back up. Okay. So the area under the curve to the left of negative 2.861 is 0.005, in other words, 0.5%. Therefore, the area to the left, that's in this particular case, that's not really a critical value because we're doing the p-test, but that's just what I have on my that's what I have on my table, so that's the best I can do. So I look to the left here and I say, oh my gosh, it's only 0.5% is over here. It's 0.005 is to the left, okay? That's to the left of negative 2.8. My test value is negative 3.157. So I'm really out there. I'm so far out there that the area to the left of negative 3.157 is even less than 0.005. So the p-value is 0.005, or less. It's less than 0.005. My alpha, my error budget is 0.05. So my error budget is 5%. What I get is a p-value that's less than 0.5%. We can easily see that the p-value is less than alpha, so we reject the null hypothesis. Okay. All right, so I hope that helps. Now, I've explained this so many times, I don't want to be redundant and have you roll your eyes, but you need to understand this. In real life, your calculator will give you the p-value, okay? But we use these tables just to become more familiar and to understand what's going on, okay? All right, so the claim is, here's our conclusion. The claim is that the average height, the mu, is less than 67 inches. So that's my alternative hypothesis. We take the sample, we find the x-bar, 65.8. Clearly, this is less than 67 inches, okay, but is it statistically significantly less? So this is what I always pick on the KFI radio talk show hosts. They would say, yeah, obviously it's less. Well, it's not obvious because it's not necessarily statistically significant. So we have to do the t-test. We have to find that the chances of getting an x-bar of this number, if the mu were really 67 inches, that the chances of getting that is very small. So you always assume that the null hypothesis is true. And then you say, well, given this data, how likely is it? I mean, should I believe that null hypothesis or should I not? Well, what I take the data, I gather my data, I calculate my x-bar, I do my t-value or my t-test, I guess I should say, and I say, hey, it's so unlikely, it's so darn unlikely, I'm going to reject the null hypothesis. Okay, so the p-value is less than 0.005. We don't compute the exact p-value from the table, you get it from a calculator, but we do not need to get the exact value. We don't need it. Okay, it's good enough to just say that the p-value is less than alpha, okay, because alpha is given to be 0.05. Remember, the p-value is that probability of getting that score, or that number, that test value, or even more extreme, okay? So it is so unlikely to get an x-bar of 65.8 that we reject the null hypothesis and we say that there is evidence to support the claim that mu is less than 67, okay? So I hope that helped. I'm telling you folks, you got to do this on your own because that's how you learn this. It's like playing the piano. I kid you not. Okay, so that's the end of this recording.